shrinkage of these polymer materials at a different temperature and at different heating rate. So in that case, you can get systematically data set of the shrinkage of this polymer at a different temperature, or you can control the heating rate. And then, if you can measure the temperature on the surface of the black hinge, then you can calculate the shrinkage of the top of these polymer materials to get the shrinkage change along the time. Then remember the geometric model in the previous slide, you can substitute this change of the shrinkage to help you to get the bending angle along the different time. So this experiment data and the simulated data matches well to each other. Of course, we are also interested in more dedicated modeling, such as finite element analysis. So we have a very strong collaboration with mechanical engineering in our universities. So I just give you very simple video demonstration of the single line foldings, how to predict the folding along the time, and this temperature change will corresponding to the color change will corresponding to the temperature change of the hinge width. So then, actually in the self-folding world, it's very grand challenging to control the folding in a sequential way, which means you can control the multiple hinge on the same polymer sheet, which folds at different time orders. So in doing that, we propose simple ideas. Instead of using black ink, you're using different color inks. So these left figures will show you different optical absorption for different color inks. So this vertical dashed line demonstrates the specific wavelengths for red, blue, and green LEDs. So take examples for the yellow color and the cyan color. They actually behave quite differently under the wavelengths of the red LED and the blue LED. So by doing that, this simple demonstration validates this concept of a sequential folding. For example, if you have a yellow hinge and the cyan hinge, so cyan is defined in our drawn graphic software, so it's kind of like a light blue color. So when you're doing the red LED first, actually the cyan color hinge will fold first. Meanwhile, the yellow hinge will not fold at all because the yellow color will not absorb the red light and convert into the energy at all. So, so opposite situations, if you change it to the blue LED, actually you can activate the folding of the yellow hinge. Meanwhile, the cyan hinge will not fold at all. So the sequential folding actually all depends on the energy. So 3 key parameters for sequential folding is the light intensity, so that is intensity of your LED use, and also the optical absorption of your ink. And so this is a 3D plot will show you how this folding time change regarding the optical absorption and the LED intensities. So by inspired of this, you can achieve a lot of complicated structures, such as nested cubes. So the small box with a green hinge will fold first if you're using red LED, and then outside the bigger orange box will fold later using the blue LED. But more interesting is that how about using the single LED, just a single wavelength? And in that case, this video, you have 3 layers of the same shape template, but with different color hinge. So when you stack them vertically and radiating the blue LED, you can actually control the folding of each layer sequentially. So we call it like a mimic of the closure, well, opposite way of the flower blossom. So some hinge will fold slightly faster because this is LED matrix. It's 50 watts. There's some hotspot specifically, so we believe that can introduce the faster folding in specific spot. So till now, you were wondering whether this method is specific or not. Actually, this is very generous. So you can even using other light source, for example, the laser light, which is a very focused light source. So this is another video. We use the IR laser. We go through this way to convert a spotlight to the linear pattern. So you can see, actually, this is folding very well and also quickly in seconds. So advantage for this, for using laser light is you don't even need to pattern the hinge at all. You can program your laser pathway to behave like a hinge itself to induce the folding. So at the end, I will just introduce all these great works has been supported by the NSF AFRI fundings. So this is our teams, actually including chemical engineering, materials, mechanical engineering, and even art and design. So we have a website, the Common Folk, actually including some videos and pictures or methods we studied, and also we learned from other resources. So you're welcome to visit. And last things, I will just leave you a question section, and the very thing. Thank you very much for your attention.
The folding reversible.
And that's actually a good question. So for this specific materials, it's not reversible, but the sequential folding I introduced at the end, it can kind of like realize a reversible folding, because if you pattern the two different color on or opposite side of the polymers, you can fold one side first, then you flip the samples, then you're using the other light source to fold the back side. So actually, when you fold back side, it's actually the flattened samples again. So that's kind of reversible. But in general, for shape memory polymer, it can be reversible using different mechanisms, especially some polymers is light activated, it can realize that. Or if you have specific crystalline areas, I know in Syracuse, like there is some research group that did shape memory polymers for, they have some works about that.
Okay, any more questions?
Hi, this is first year graduate student Preeti Saul from Syracuse University. I was just curious, a statement that you made that said it folds like a flower. So is this the mechanism how flowers that bloom during daylight?
So maybe I talk too fast. So actually there's a three piece of polymer sheets. They stacked together vertically. So each layer has a different color hinge. So that causes the sequential folding. So the top layer will fold the fattest. So that's why you can see this kind of like flower blossom. Yeah.
I mean, is it a biological process that you have some kind of a material that does a similar behavior in real flowers? I mean, I'm just curious.
So, sorry, can you repeat that question?
So do real flowers have some kind of this material that behaves in the same manner when exposed to sunlight?
Yes, so we're not very knowledgeable about biological, how the flower things, but we do saw some review articles discuss actually flower blossom and closure. It can be different mechanism. So either the major mechanism is light and temperature. So some flowers blossom really depends on the light. So they will close it and after the dark, when in the darkness. And some really depends on the temperature. And that's why you see more blossom maybe in the spring after the winter. And some few it depends on the humidity and moisture of the environment actually. So in our case, I would say it's more like a temperature dependent.
One last question.
So, how do you, so can you control it to fold into different angles for the same
Yes.
hinge?
So by you define the hinge width, you can control the folding angles as well.
So I mean, for the same hinge, can you like fold it to this angle and later to another angle?
I think depends, because it all depends on the shrinkage. So I think if you're using the same material, same shrinkage, and the same hinge width, you will get the same folding angles. You have to change the hinge width to get different angles.
Thanks.
Okay, thank you again. Okay, our next speaker is Rocklin from the University of Michigan.
That sound good? Good afternoon, everyone. I'd like to thank the organizers for this wonderful conference. My name is Rocklin. I'm from the University of Michigan. I'll be discussing programming smart matter via topology and how we can use topological states of matter as a design principle that will give us materials with desirable mechanical properties. I'd like to begin by acknowledging my collaborators. Vincenzo, you've heard from already. Brian will be speaking later, and Zhao-Ming's chairing the session, so she gets to cut me off when I go over time. So the question I want to address today is how we can create and control states of matter that have inherent mechanisms. So this is in some ways similar to, but in some ways different from what happens when we try to define and create a mechanical structure at the macro scale. So at the macro scale, we can precisely engineer parts, and we end up with something like a robot arm, or a water wheel, or a simple lever that generally supports force along certain stiff directions, but it also has free motions where it costs very little energy to rotate it about its joints. And this is what we use in all sorts of ways in modern day life to control motion and force and to transform one type of motion into another type of motion. When we go to the micro scale, we're more generally involved with self-assembling some structure that is more or less homogeneous, it's subject to disorder and to vibrations. And so this presents certain challenges, but we still want to do the same sort of thing. Namely, we want to support force along certain directions, but we also want to have certain motions that it is allowed to make, certain joints around which it can rotate. And what we'll see is that topological states allow us to create motions that are robust, but also changeable, and that these states give us direct mechanical properties. So, topology is sort of a general phrase that means different things to different people. I'm using it to mean properties of the system that depend on its global structure and are preserved under continuous deformations. It's a fundamental way of characterizing different states of matter. And in general, we're going to be talking about some winding number. So if we have some sort of phase field, it has to come back to itself if we draw a loop in space. But it can come back to itself modulo 2 pi, because a phase of 2 pi isn't physical. So we can have a winding number of 0, +1, -1. These are different states that in general will have different properties. So probably the most famous example these days is topological insulators, where you have a winding of an electronic phase field, and that determines whether you have protected conducting edge states. The simplest example I like is just of solid objects, where you don't have to think about phase fields or do any sort of reciprocal space calculation. You can just say, I have a loop of some substance, and I have a loop of another substance, and they either don't wind around each other, or they wind around each other once, or twice, or -1 times, depending on how you define things. And that can determine useful things, like whether your bicycle stays localized when you leave it on the bike rack. If your lock loops through the bike, it's localized. If your lock doesn't loop through the bike, it's not localized, and someone can remove it. Your trajectory can be in time, so if you have a magnetic field trajectory, this is a recent experiment on topologically protected transport, and depending on the topological number associated with the winding of this magnetic field, these particles either just vibrate in space on a single lattice site, or they move one lattice site around each loop. And then finally, what we'll be focusing on in this talk is when we're talking about phonon phase fields instead of electronic phase fields. So Chen already introduced this gyroscopic system. So that is, in a sense, an active system because the gyroscopes are spinning. What I'll be talking about today is an even simpler system, not really active, where we just have a mechanical frame. So we have a certain number of particles. The particles can move around, but they have permanent bonds connecting them to one another. It costs finite energy to compress the bonds or to extend the bonds, but it doesn't cost any energy to rotate the bonds against each other. So this is a sort of structure that can generally support stress, but also has certain free motions, even nonlinear free motions. And when I draw it, I will often just draw these as solid triangles rather than drawing out all the particles. So this is scale-free theory. So really all we need is something where we have relatively stiff beams relative to fairly free hinges. And when we talk about going down to the microscale, there are a number of techniques that we can do this to make mechanical metamaterials very small. And we can do lithographic techniques to get this oxidic material, this material that has a negative Poisson's ratio. We can also do self-assembly of colloidal Janus particles. So these particles have attractive patches that form bonds, but they also have repulsive bands in the middle, which leave open pores in between the bonds that give the particles free space to rotate into. So there is an index theorem that governs such mechanical frames. It goes back originally to James Clerk Maxwell, writing in the 1800s, who was concerned with making sure that bridges don't fall over. And he noted that whenever you include a site, that site carries with it a certain number of degrees of freedom, 2 degrees of freedom in 2 dimensions. And when you add in a beam in between them, that's a constraint that can take away a degree of freedom. So you have this counting, you count out the number of sites times the number of dimensions, you subtract off the number of bonds. That doesn't necessarily give you the zero modes though, because depending on how your bonds are structured, here each of these bonds are independent, but if I move one of the bonds from the top square to the bottom square, the top square becomes floppy. I've added a zero mode, but the cost of that is that I've also added something called a self-stress, where in the bottom square, I can add tension to each of the bonds in such a way there's no net force on any site. So to create a zero mode, to create a mechanism, a way of distorting the frame, I have to either remove a bond or find some way to make it redundant. And in particular, we're interested in Maxwell lattices or isostatic lattices. I'm not going to make a distinction between the two in this talk. And these are lattices that are just barely at the point of being rigid. So if you look in the bulk in 2 dimensions, there's a coordination number 4. That means for each degree of freedom, there's a constraint. So then we should have zero modes only if some of the constraints are redundant or if we're missing some bonds. But if we have open boundary conditions for a finite lattice, we are missing bonds. We're missing bonds at the boundary. So if we have a lattice like the deformed square lattice here, which has bond topology of the square lattice, but has bonds of different lengths, so you don't have straight lines, or if you have the deformed Kagame lattice, where again you don't have all equilateral triangles, so you don't necessarily have straight lines, the question becomes, where are your zero modes? The index theorem tells us that we have to have some number of zero modes from the missing bonds at the edge, but it doesn't tell us where they are. Intuitively, you'd think they should be evenly distributed around the edge, because that's where the bonds removed were. But what Kane and Lubensky showed was that this is not always true. They showed that such mechanical frames can be topologically polarized, meaning that you take some of the zero modes that should exist on the left edge, and depending on the structure of your lattice, not the composition, but the structure, how long each of those bonds are, you can actually find a lattice where the zero modes that should be on the left edge have been moved over to the right edge, leaving no mechanisms existing on the left edge. And this is a physical quantity that's determined by a winding number of the phonon phase field. So it's determined by the structure of the rational modes, even though we're talking about a purely mechanical phenomenon that comes out of it. in addition to these edge modes, Maxwell lattices always have what's called a guest mode, after Guest and Hutchinson's work. And they showed that if you have a Maxwell lattice with a crystal structure, there's always some way of changing the structure without stretching any of the bonds, so that you're changing the size of the unit cell, but you're not costing any energy. If you have a lattice that's not a Maxwell lattice, that's not true anymore. You can certainly have stable mechanical frames if you put in enough bonds. But even in such a lattice with extra bonds relative to a Maxwell lattice, if you look at the panel all the way on the right, you can have redundant bonds. So on the right, each tile is a parallelogram, and this means that there's a way still to uniformly rotate it despite the fact that it has more bonds. So let's look at a quick video of that. So here I'm twisting the triangles against each other. So this is not costing any energy because I'm not stretching any bonds, but I am changing the structure to a nonlinear degree. So now let me show you, this is us actually making the material. We call this a transformable topological mechanical metamaterial. And everyone on this project is a theoretical physicist, so this is not self-assembled, it's not microscopic. We're taking advantage of the scale-free nature. We made this out of kinetics, plastic toys, and these are rigid triangles that are joined together at literal hinges here. And we're at the Maxwell point, so you can see we're pressing on the bottom edge, and it's distorting. We've activated a zero mode, we've activated it non-linearly even. And we go around to the other side, we try the other edge. This is a regular Maxwell lattice, so each edge is floppy because it's missing bonds at the edge. And now the next thing we're going to do is we're going to activate that guest mode. We're going to change the structure of the lattice. And the way we do that is by controlling the whole edge. So we've inserted metal rods at the edges, and now we're just pulling on them. And since the metal rods are straight lines, this is going to still force us to have crystalline order, but we're changing the lattice spacing. And what we're trying to do is we're trying to topologically polarize the lattice. So we're trying to take zero modes from the bottom edge and move them over to the top edge. What we're also doing, though, is we're introducing a certain amount of disorder, because as you can see, the rods are wiggling back and forth. We only have so many hands on this project, and the rods have a certain amount of give in them. And really, almost to a deliberate degree, we've created something that is in a very uncontrolled environment. So now this is really our first attempt. We're going to see what happens. I'm going to push on it just like I did before. And you can see it's actually sliding across the table now. Before it crumpled, now I haven't added any extra bonds to make it stronger. All I've done is change the angle between bonds, but it's gotten much stiffer. Now it won't crumple. Now it's strong enough to slide across the table. I go over to the other side. This is the side that should have twice as many zero modes. It's still floppy. In fact, it's even floppier because it has more zero modes, so it has more ways it can deform. So what's happening here? So if we go back to our actual calculation, we say that there should be, to start off with, there should be zero modes, the red arrows and the black arrows, on the top and the bottom. Once we change the angles enough, though, we get to the so-called critical lattice, where the red arrows aren't decaying anymore. They're not edge modes. They've entered the bulk on the upper right-hand corner there. And if we keep going past that, the red arrows are now on the top. Now we have two modes on the top, one mode on the bottom. When we have a zero mode on the bottom, if we just press on that bottom and we try to indent it, and we're doing this in a simulation now, this is a simulation of a 60 by 60 lattice, it costs essentially zero, the edge stiffness is essentially zero, but if we go over to the point where we've removed that zero mode, now what's happening is we can't just twist the triangles against each other, we have to actually stretch the triangles, and that costs a finite energy and gets us exponentially more energy cost to indent the edge. Okay, so this is just everything I just said all on one slide. We go through three critical angles where we have straight lines of bonds. That means we have zero modes in the bulk. And we change the topological polarization 3 different times. I'm running out of time, but let me just say really quickly that we've also figured out how we can take these zero modes from missing bonds on the edge, and we can put them in the bulk. So we can take these topologically protected instabilities and actually use them to actuate not just the boundary, but the whole bulk of the material. And we can manipulate those modes, which we call valve modes, with the guest mode as well. So we can use the guest mode to put them in, to tune them to a different wave number, and to remove them as well. I'm out of time. So topological invariant is a way of determining the edge stiffness. That has physical consequences. And we can use these global mechanisms, the guess modes, to change and control the topological properties and therefore the edge stiffness. And then finally, we can take the topological mechanisms from the surface, and put them in the bulk.
Okay, just one quick question. Okay, so let's welcome the next speaker. Thank you.
I didn't try to find it. I was afraid I'd put something.
Okay. So thanks to the organizers for having me here. Last couple of years I've been having lots of fun playing with mechanical metamaterials. And well, I'm not going to tell you anything about this particular example except to give you an idea what this is. So it's a piece of rubber and we made holes in it. And then it does something interesting when you push on it. Okay, I'm not going to tell you what it does. But what I want to talk about is the question, well, how do you come up with a design for these sort of things? And in this particular case, I just had an idea and it was completely wrong, but then, you know, when we started playing with it, it turned out to be interesting. But we would like to do something more intelligent, and I would also like to have a more intelligent laptop maybe. Okay, we'll see. So if you go to the interwebs and you look for mechanical metamaterials, you find all these examples. And, okay, well maybe we'll get there in the end. I'm not quite sure. Okay, including this example of Vincenzo. And you know what you see here is that these are always structures with a unit cell, the periodic structures. So what do? You design a unit cell and you tile space, often a two-dimensional space, and then you're done. And you know this sort of helps us because you know designing a unit cell, that sort of you can often do this sort of intuitively or quasi-intuitively. But if you think of more complicated functionalities, you typically don't use mechanical, you don't use periodic structures. So, you know, it's very hard to make a periodic watch, I think. So often when you try to make something, you have multiple building blocks that you assemble together to get a functionality out. And in particular, if you want to have something which is not spatially homogeneous, you need to do something else. And so this is what this talk is about. And so the talk was called Flux-related metamaterials. And does anybody know what flux-related means? Of course not, because it's a stupid word that we made up. But it's about fluxels, okay? What is a fluxel? Well, it's a flexible voxel. So you know what voxels are. So this is our building block. It's a cubic piece of rubber, and it's soft, so I can push on it and then it deforms, okay? And the way we think of these deformations is really sort of the thing is bulging outward or it's sort of going inward. And the question now really is, how can I assemble these voxels together to get something interesting? Because the point of this particular building block is it's anisotropic. So I can take these building blocks and I can orient them in different directions. Okay? So let's call them X, Y, and Z, so red, green, and blue. So these are the voxels. And now the idea is I want to make a metamaterial like this maybe. Okay? And would this give me something interesting? Okay. So let's see how this works. And I should also say this is joint work with the group of Yar, who's in the audience here, and whose name I just clicked away. Raise your hand, Yar. He did all the smart theoretical. Okay, so this is the building block, and if you deform it, well, you can think of the deformations as sort of spins living at this block, or you can think of these blocks, you know, symbolically as little cubes with things sticking out. I'm just going to use the computer, I think. So when you assemble many of these building blocks together and you squeeze them together, And so this is, let's say, the normal metamaterial game. So you make a periodic structure, you squeeze it, and at some point you see this collective pattern deformation. And you could already be very happy with this, but this is sort of the first step, and then I'll show you how to make different structures. But it's useful for a moment to think, why do I get this deformation mode? So let's think of, this is the deformed state, and let's think of how all these deformed building blocks fit together in 3 dimensions. Okay, and this is sort of a simple case, so I think most of you can see how it works. So in the middle I'm going to show you sort of what the real space blocks look like, and to the right I'll show you the symbolic representation. And it's clear that I can fit a deformed block, let's say, that's deformed in the opposite way next to it. I can also do that below and behind. And when you think about it, you can see you can tile space with all these deformed blocks. Okay? And that's the reason that this is sort of the low energy deformation that you see. Because the individual building blocks, they want to deform in this way, and they sort of can do that also. So now the question is, of course, I have these building blocks, can I make an aperiodic stacking? So can I make more complicated materials? And so what we're going to do then is think of these building blocks. And again, I will color them by their orientation, but it's really the same building block that I just orient differently. And I know already what their pattern of bumps and dents is, and I just have to solve this 3-dimensional puzzle for them all to fit together. And so if you just think of 2 building blocks, if I take a red and a green building block and I start to deform them, well, if they deform in the right way, sort of things fit. If they deform in the wrong way, they don't fit. Okay, so you always need a bump and a dent to go together. So these 2 guys are bad and the other ones are good. Is that clear? Okay, so we had this periodic state. Let's now see what happens when we take differently oriented building blocks and try to fix them together. So this is one configuration that I could try to make. Okay, so now we're going to see does it fit. So do all the spins in some sense fit, or do all the bulges and dents fit. So let's say that this guy is shaped like this. So then I know what this one is going to do. I know this one. And that implies also that the spins here are like that. But now I look here, okay, so that doesn't work. So that is sort of an illegal configuration. Okay, so if I would make this cube and I try to deform it, it wouldn't work because all the faces sort of are unhappy and the system gets frustrated. And of course, aperiodic systems are typically frustrated. This is what you normally expect. If you take, take a jar of sand, the system is aperiodic, but it's also very much frustrated. But the cool thing about these metamaterials is that I can place all my building blocks precisely where I want to get something interesting. And so there is now an overlap between frustration-free systems and aperiodic systems. And this is just one out of trillions of configurations that you can think of. You probably don't want to go through all the rules, but okay, it works. Okay, so there are ways to assemble these building blocks to get a frustration-free but complex state. Now, very briefly, if you start with a little patch like this, where all the spins are compatible, you can stack different layers on there. So, for instance, you can take the same layer and it all fits. But there's also other guys that fit. And you can build up your metamaterial basically motif by motif. You can stack them in all sorts of different orders. And that means that you can make periodic things or quasi-periodic things or aperiodic things. And if you think about it a little bit harder, you realize that the only thing you need to know is what the deformations at the surface are. Because once you know it at the surface, these rules propagate inside the bulk. Not so important, but what is interesting is that this allows you to sort of estimate the number of distinct L by L by L stackings I can make. And these dots actually represent exact calculations, and these are large numbers. So if you take a cube of 14 by 14 by 14, you get an incredible amount of all distinct metamaterials, where all these building blocks are a little bit different. Okay, so what can you do with that? Well, even if you missed the rest of the talk, this is sort of the thing we're most proud of. Some of you have seen it. So this is an actually 3D printed metacube. It consists of 1,000 unit cells, and they're all oriented slightly differently. And now we're going to squeeze it and see what happens. And this was carefully designed, okay? To do just one thing. Right, so you can basically program the shape it's gonna take. And well, I don't think the world is necessarily waiting for a smiley cube, but you can start to think of this as a template for shape-changing materials. Because at least if you just design one face, you can get any pattern you want. We know precisely how to do this. And even if I design this face, there are still a number of different ways of doing that. So it gives you a design principle to have shape-changing materials. It also gives you some interesting mechanical pattern recognition. And I'll very briefly go through it, but we made a somewhat smaller cube, also with a little smiley face. And then you just squeeze it between two patterned surfaces. And of course you can choose to have the pattern on the surface to be compatible with the internal structure of the cube or not. And you can imagine if the thing is not compatible, well, the system gets frustrated, and so effectively the cube is stiffer, and that you can measure. And the interesting question now is, can you understand the stiffness? And so what you would expect is, you know, the more your pattern is different, the stiffer your cube is. But it's a little bit more subtle than that. So if I take a pattern, so here I have a pattern where I have 12 misplaced pins, but they're all sort of nicely together. And here to the right, I also have 12 misplaced pins, but they're all over the place. And what is different there is that you basically can think of sort of the circumference of the domain wall separating these two. And it turns out that this one is also important. So we actually did 136 experiments where you vary the number of misplaced pins that we call A, and the circumference, C. So these are all the combinations that you can make. And then for each of them we measured, and we also in computer simulations measured the stiffness of the cube. And we indicate that with a little circle there. So you see there's systematics there. And the nice thing is if you take the sum of A and C, basically all your data sort of collapses. So this cube is actually really a simple machine, and it does something weird. It takes a pattern, compares it to its own internal pattern, and its stiffness tells you then how many pixels are off and what was the circumference of the pixels that were off. So we think of this as a machine material. And so to wrap up, the idea is to start with a very small set of building blocks, which are anisotropic, and you combine them together, and combinatorics is still sort of doable. You combine them to get all sort of new aperiodic materials, and in particular aperiodic but frustration-free materials that can do all sort of crazy things. And to, just as an, well, almost like a segue to the next talk, we've also been doing this for origami. There it's much more complicated because we get 34 different tiles that you can orient in all sort of different ways, but this allows us now also to generate, you know, trillions of different origami patterns. And I think there are many ways to extend this work further. Thank you.
Questions?
So is it possible that you have your cube set up so that you press down on, say, 10 of the, I don't know, 10 of the squares, you get a smiley face out, and then you press down on a different 10 of the squares, and you get a sad face out?
Yeah, not yet. So this is clearly the next goal, because what the world really needs is, you know, bifacial smileys. But but indeed, I think it's a good question to think of multifunctionality. So in this way, you know, this strategy wouldn't work. So what you need to do is probably remove some of the cubes so that you have like multiple modes in your system. And this is precisely one of the things we're thinking of, how you can do that in a rational way so that you can put more information in your material.
Any more questions?
Can you define the Shannon entropy for your cube?
Yeah, well, if I probably remembered precisely what the Shannon entropy was, I could. So this is what is it? You count the number of states.
Yes.
But it's just like the log of the number of states or something, because that we've done.
No, it's not information.
Well, if you think of the amount of configuration information in terms of the amount of you know, configurations, that this is the answer. But if you take a single cube, right, a single cube, it's just one of them, And now, actually, there's an interesting question. If I start to push it in different ways, how do I count the states? But it's not so clear that that is sort of a discrete process. So then I don't know. But this is an interesting thing to think about.
Yeah, this is a little like the spin ice.
Yes.
For every cube, you have certain numbers of in and out.
Yes.
And then for each ground state, you can consider the excitations.
Yeah, now this is of course how we did this counting. So we mapped it to an ice rule, and by the time I sort of realized it was something like that, I talked to Jar because he really knows how to do this and to count this. And indeed, you can ask yourself, if I start to frustrate the system, is this like going away from the ground state of the spin ice? But it's not entirely clear if the mechanics really work the same way as the spin ice there. But that's some way of thinking about it. Yes.
So, what are your plans for going beyond physics?
Well, the first thing, the thing that I really want to do is go to multiple functionalities, and I think the interesting way of doing that is really thinking about being able to program the material, which means that you need to do things which are non-commuting. So whether I first push from one side or from other sides should matter. So what I really imagine in the end is that you would be able to make some sort of object that by pushing from the sides I can program a certain function, and it can act as a logical AND gate or an OR gate or something like that. So I can make sort of really information processing devices. So that I would think would be interesting.
Okay, let's send Martin again. Our next speaker is Chen from UMass-Amherst.
This one's also a laser print? Or maybe I'll just use this one. Oh, yeah, I'll just use this one. No. Well, I just want to use the pointer. I think I'll use the computer to control it. Okay, so hi everyone. I'm Brian Chen. I'm from UMass-Amherst. I'm a postdoc working with Chris Santangelo there. And really excited to be at this conference to tell you about some work that I did. Unfortunately, I don't think it's particularly active. And as for being smart, I'll let you guys decide maybe. So I think, as we all know, origami is sort of a very beautiful and old art form, and the sorts of things that people are able to do now is really kind of amazing. And you know, there's been a lot of interest, sort of, as Martin pointed out, you know, in all sorts of different mechanical metamaterials. So again, you know, these are structures whose properties are not necessarily coming from the substance that they're made out of, which particular polymer or chemical, but rather, you know, the functionality is coming from something in the design of the unit cell, some geometry or connectivity there. And what I mean by mechanical metamaterials is something that has some interesting, useful physical property coming from some flexibility. So really, you know, the fact that the unit cell can, say, go between different states or have different sort of tunable amounts of flexing, you know, that's the sort of thing which I find very interesting. Of course, people have sort of been thinking about making materials out of origami for quite a while. So here's sort of an image that I took from kind of like a art and design blog. This sort of idea has also sort of become popular in certainly the scientific literature as well. Here are a number of interesting examples of structures starting from the Miura-Ori to some other kinds of structures that have multiple branches, and also certain sort of bistable structures that can be, whose bistability can be tuned. But there's sort of a ton of other possibilities out there. So, you know, this is a search I did a few years ago on just some random photo website. And, you know, the thought that I had then, which I think is still true, is that, you know, you could probably take any one of these structures and write a very nice paper about it. Okay, so I'm not going to tell you about, I'm not going to write one paper for each one of those. I'm a physicist, I'm kind of lazy, so I want to try to understand if there are some basic principles that can say something about all of these structures at once. And being a theoretical physicist, really, what I'm searching for maybe are some interesting models that can do kind of cool things. And so let me introduce something that, an idea that Zeb sort of talked about a little bit before, which is the idea that the coordination number, or sort of the connectivity of a structure, and sort of the idea that the number of degrees of freedom and the constraints in the system can really determine a lot of its properties, at least mechanical properties. So on the left here and on the right, I sort of have two extremes, so two different phases of matter, I guess. So think of these blue dot disks as kind of points in the plane, and on the left-hand side, they're not connected to each other at all, so I could imagine just taking any one of these and moving them. This thing has a lot more degrees of freedom than constraints, so it's very, very floppy. On the right-hand side, I've tied them all together with these red bars, and so this is a completely rigid object. We might imagine that interesting things can happen if we look at systems that are somehow in between. So if we sort of just connect, if we imagine that these bars can sort of freely rotate at these points, then here I have a structure that's sort of part of a square lattice. And an interesting fact about this is that the number of deformations of this is controlled not by the area, but rather by, it's neither completely rigid nor completely floppy, somehow it's something in between. The number of deformations it has is controlled by sort of the surface area of this thing. And these are interesting enough that we've, that some jargon has been introduced for these. So these are sort of known as Maxwell lattices, again after James Clerk Maxwell, who sort of first used this idea of counting to say some interesting things about mechanical frames like these. And so what's the connection to origami? Well, it turns out that origami structures very often have this critical coordination property. In particular, triangulated origami has this property. So let's consider some periodic origami sheets, triangulated origami sheets. So periodic because, I don't know, we want to make some kind of a metamaterial out of this. So we have two simple equations. I promise this slide, I think, is the only equations that I'll be showing. So every face of this thing is a triangle. So there's, if we try to count the edges in the system, then we'll have 3 edges for every face. But we're sort of double counting the edges because every edge is shared by 2 faces. So we have this equation. We also have the fact that the Euler characteristic, this particular combination of the number of vertices, edges, and faces is equal to 0. And what this gives us is this equation for 3 times the number of vertices is equal to the number of edges. And we think a little bit about degrees of freedom and constraints. We find that this is actually saying that in a structure like this, the number of degrees of freedom and constraints are equal in the bulk. So, the idea here is that we model this origami structure so that each one of the vertices has 3 degrees of freedom. It can translate in any direction it likes. And in the special case of where we have triangular faces, it's just, we don't have to model these as rigid plates. We can just say that we have length constraints as the edges because a triangle made out of 3 points can't bend in any way. So we find that these structures exactly have this critical property. And what's more, triangulated origami plays kind of a special role. So oftentimes when one is looking for critically coordinated structures, you have to do some kind of a tuning to set your coordination number exactly to a critical one or the pressure or something. But the triangulation condition is very natural because this is somehow the most floppy that you can make in origami. If you have some kind of a origami tessellation, you could always, if you have some plates, if you have some faces in there which are not triangles, you can make your structure more flexible by sort of adding diagonals. And this is sort of the upper limit. You can't make anything more flexible without starting to add some holes in the structure. So what is this? What is this criticality condition good for? Well, So what I'll be telling you about is a property that Zeb already told you a little bit about, which is the topological polarization that was introduced by Kane and Lubensky. And so their idea was that if you have one of these critically coordinated structures, you can define a polarization in these structures, sort of akin to an electrical polarization. However, instead of having positive charge and negative charges, what we're separating are degrees of freedom and constraints. So this is sort of like a cartoon picture of the polarizations in this structure. And the fact that we have an excess of plus charges here means that we have a domain wall where we have an excess of floppy modes. And on this side, we have an excess of states of stress. And by using this idea, we can design structures with localized floppy modes or sort of transformable behavior where these properties are protected to a very robust degree by the topology. Okay, so how do we apply this to origami? Well, let's think about sort of one of the simplest structures that we can imagine. So some one-dimensional structure made out of just a strip of fourfold vertices. So we kind of have a backbone here, and each one of these vertices has 4 creases coming out of it, and it sort of just continues in a periodic way like this. So the first question is, well, how do we define a polarization? It turns out that there are some subtleties here. So the polarization relies on sort of looking at the linear response of structures. But if you think about origami for any amount of time, you realize that the flat state has a very, it's very, very singular in a way. So because it's flat, sort of to infinitesimal order, you can move any of the plates and it won't stretch anything. So this is realized sort of in this picture of a single rigid vertex. So if you just have a single one of these vertices, so this point here is the flat state. And I'm drawing here, these curves correspond to all the different possible configurations that don't sort of bend or stretch any pieces of it. And you can see that there are 2 branches that pass through the flat state. So this is sort of a signature of this singularity. So to make a long story short, it turns out that we can define a quadratic displacement, not the usual sort of linearization that one would use to define a polarization in this system. Once you have that in hand, it turns out that we can also find a phase diagram for these structures. So this is a phase diagram in kind of design space. So beta and gamma are these 2 different angles that we have in the system. And the 2 phases here correspond to the 2 different topological states. So again, remember that the polarization counts the number of floppy modes or the degrees of freedom on different sides of the system. So in this simple structure, we just have, it just tells us whether the right edge of the system is soft or the left edge of the system is soft. And because what we're doing here is topology, it turns out that this is robust enough to survive the transition from sort of idealized math models to real life. So here's a 3D printed structure made by Ying Liu when he was working with Itai Kohn. And one can see, this structure, as predicted, has one side which is soft and another side which deforms much less. Okay, so this is the story for 1 dimension. Turns out in 2 dimensions, some things are the same and some things are much trickier. So so it turns out that there's sort of 2 classes of structures you might consider, those with holes and those without holes. And it turns out with holes is somehow a little bit simpler, or it behaves more like those in 1D. So we can find a polarization for structures with holes and then sort of do things with them. So here are 2 structures with holes that differ by having a polarization. When we create a domain wall between them, we find that the lowest, that we get a nearly 0 energy mode here, which corresponds to kind of a wrinkling at this domain wall. So one could imagine using different domains and programming domain walls to have sort of programmed wrinkles in structures. When we have 2 structures that have the same polarization, the lowest mode looks more like what we would expect, kind of like acoustic bending modes. So something interesting happens if we go back to origami structures that don't have holes. Turns out as much as we tried sort of looking at random structures of all different sorts, all different crease patterns, we could not find any that could be polarized. And we don't really understand this at all. So I've run out of time. I'd just like to say a little bit about what we're thinking about now, which is nonlinear deformation. So one of my favorite pieces of work that I've done recently is to think about linkage structures and their nonlinear deformation. So here's sort of a toy model of the Jacob's ladder toy that some of you may know about. You could ask the same question about these origami structures. Do they have interesting nonlinear deformations? Turns out this one doesn't really. So it does deform if we kick this soft mode, but it doesn't propagate as this toy does. We've also been thinking about sort of bending deformations of these structures and how that relates to elasticity. If you're interested in any of these things, please talk to me afterwards. And I'd like to thank you and also sort of funding sources. We haven't found one yet. You'll be the first person I've tell.
If you see the slide that Brian showed, that little thing they showed, the edge mode becomes a propagation sausage. I was asking whether you can add that.
Okay, are there any more questions? If no, that's our next speaker on the section is Cecilia from
So we're going to switch topics a little bit, and what I'm going to tell you about in this talk is some recent work that we've been doing in my group, trying to think about how we can use geometry and confinement to perhaps control the collective motion that is known to arise in dense bacterial suspensions. And this is work that was done primarily by my postdoc, Maxime Teilhard, and my two graduate students, Roberto and Brant. Okay, so I don't need to give much of an introduction to this audience, but this is my obligatory introduction slide to active matter. So you all know what an active matter system is. It's a suspension or a collection of particles that are able to convert energy, typically some kind of fuel like ATP, into mechanical stresses. And there are many different examples of active matter systems in biology and in engineering. And today we're primarily going to be thinking about bacteria. Some interesting properties of the system is that, well, they're non-Brownian for the most part, or nearly non-Brownian, so they're very far from equilibrium, so you can't really use typical tools from statistical physics to describe them. And what I'll try to show you is that fluid mechanics is one tool that is quite useful in this case. And some features that are observed ubiquitously in a lot of these systems, there's self-organization that takes place, collective motion, and you also have very large number density fluctuations. So these are just a few pretty pictures of some examples of such systems, but we're primarily going to be thinking about these two, A and B here, which are bacteria. So there's a lot of work that's been done looking at the collective motion in bacterial suspensions in the bulk, and this is some observations that have been made. So this is a typical movie of a suspension of bacteria. Each little dark rod is a bacterium. It would go more or less in a straight line if it were by itself. But as you concentrate them, it's well known that you get these large-scale flows that are chaotic, that look like turbulence, even though there's no inertia on these scales. So some features are typical in the experiments are, again, large-scale coherent flows, strong density fluctuations, there's strong mixing, and strong diffusivities as well. So this is what happens in the bulk. What we're more interested in looking at today is what happens if you confine these suspensions, let's say in a microfluidic device. So what happens in confinement? First, we can think about the dilute case, and this is something that's well known. If you confine self-propelled particles, they tend to go to boundaries. And this is seen in many microfluidic experiments. One mechanism that was proposed a few years ago by Eric Lauga is the following. If you think of one bacterium swimming next to a wall, it exerts a forced dipole on the fluid, and the wall essentially has the effect of of an image swimmer on the other side, which creates an opposite dipole as well as a couple of other singularities. And the effect of this dipole is to attract the swimmer towards the boundary. While this is a true effect, what I'll try to show you is that this is not, in my opinion, the primary mechanism leading to accumulation. You can get accumulation without any hydrodynamics. What happens now if you concentrate particles in confinement? There are a few recent experiments that have looked at this, primarily from the group of Ray Goldstein. And this is one experiment that appeared a few years ago where they looked at a dense drop of bacteria, which is shown here on the left, and which is squeezed between two flat plates. And this is what they observed. Instead of seeing the collective, the chaotic motion that I showed you a couple of slides ago, what they find is that the bacteria organize into a vortex. And if you look very carefully, in fact, it's really a double vortex. There's a core that rotates in one direction, and near the boundary, the bacteria are moving in the opposite direction, which is something that you can see by doing PID. And this is typical velocity fields where you have this counter-rotating boundary layer. So we'd like to explain where this comes from. Other related experiments more recently have looked at periodic channels. Again, from the group of Ray Goldstein. This is the thesis work of Hugo Violent, who looked at these periodic racetracks, again with dense bacterial suspensions, and what they observed is that the suspension spontaneously starts flowing in one direction. So it picks either clockwise or counterclockwise, and then it continuously flows. So essentially you have a pump. So this has been observed in bacterial suspensions. On the right, this is another recent experiment that looked at sperm. So sperm also exhibits the same dynamics. When you increase the density of sperm in a periodic racetrack, there is a bifurcation to net pumping. And another feature that was observed in the experiments is the appearance of traveling waves, traveling density waves at high volume fractions. So again, we'd like to explain these effects. Okay, so let me take a step back and think a little bit about what each bacterium does in these suspensions. So we're going to be thinking about E. coli, the other bacteria exhibit similar dynamics. So you're all familiar with E. coli. It's a rod-shaped bacterium, and it swims by rotating its flagellate bundle. So this is a simple picture of E. coli. By rotating its bundle, it exerts a thrust on the fluid, which I'm calling FP here. This is a propulsive force. And this is what pushes the bacterium towards the right. But now the cell body is being pushed through viscous fluid, so it experiences a drag force. Right? And if there's no net external force on the particle, these two forces have to balance. So the thrust is exactly balanced by the drag, and you can think of this as a force dipole. This is the simplest representation of such a particle. And this is indeed a good model. This was tested experimentally by Knut Drescher, again in the group of Goldstein, where they measured by PIV the flow field around individual bacteria, which matches the flow field of the Stokes dipole quite well. And you get the characteristic decay of the velocity is 1 over the distance squared from the organism. The sign of the dipole is negative. Sigma naught here is the prefactor of the velocity, which you can extract from these velocity fields. And it's negative, which is the signature of a pusher particle, which pushes itself through the fluid using its tail. Okay, so that's our simple model for one of these particles. Now we can think about describing a collection of particles. And there have been a number of models that have been proposed over the years, including by some people in the audience. This is the one that we're going to use. So we're going to use a continued model, and we're going to describe the suspension using a distribution function psi of x, p, and t, where x is the position of one swimmer, p is a unit vector that tells you about its orientation or swimming direction, and t is time. Particles are conserved, so this distribution function satisfies the conservation equation, which is shown here, where the rate of change is balanced by fluxes in position and in orientation, and this is how it's normalized. So this distribution function lives in a high-dimensional space. It's got 5 degrees of freedom, x, y, z, plus 2 angles for the parametrization of p in addition to time. And so it's sometimes more useful to think in terms of its moments. So this is what I'm defining here. So here the brackets are an average of orientations. So if you average a distribution function of all orientations, you get the concentration field, which is a scalar. Then you can look at the average of p, which gives you the polarization. This is essentially the mean direction of swimming. And you can then take the second moment, from which I remove the trace here, which gives you a second order tensor, which is a pneumatic tensor, which tells you about the alignment of the particles, irrespective of the direction in which they point. So we're going to be thinking about these variables a lot. To close the equation, we have to specify the fluxes, x dot and p dot, which you can think of as the center of mass velocity and angular velocity of one of these particles. And so the center of mass motion includes components from swimming in the direction of the unit vector p. There could be convection by the flow, which could be an external flow, or the flow generated by the swimmers themselves. And you can also add translational diffusion. P dot is the angular velocity, and this first term on the right-hand side here is known as Jeffrey's equation, and it tells you how one particle rotates in a flow field, where E and W are the rate of strain and vorticity tensors associated with the velocity field U. And finally, you can also add rotational diffusion. So that's our basic model. And here we're thinking really about the flow fields that are generated by the swimmers themselves. So we need to specify how we calculate this U of x here, which is the velocity driven by the swimmers. So as I showed you earlier, each swimmer essentially exerts a force dipole in the fluid. Based on this idea, it's easy to come up with an expression for U. If you think of a single swimmer, this is the equation for the flow field that it creates. So these are the Stokes equations, and I have a forcing term on the right-hand side here, which is the forcing term corresponding to a force dipole. You can easily see where the gradient of this delta function comes from. You would take two equal and opposite point forces, close to one another. So this is a flow field due to one particle, and there's one parameter that I think I mentioned before, which is sigma naught, which is the dipole strength, which is negative for pushers such as bacteria, but there are other particles that have positive dipoles, for example, the microalgae, Chlamydomonas. Okay, so this is for one swimmer. Now we have a collection of these swimmers, so what do we do? Well, we simply take a convolution of this forcing term with a distribution function. And after a little bit of algebra, you get this expression for the momentum equation. So this is the Stokes equations, and the forcing term is a divergence of a second-order tensor, which we call the active stress. So essentially, the effect of these dipoles is an extra stress in the fluid. And this stress tensor, which I'm calling sigma p here, is simply the dipole strength times the pneumatic order parameter. Right? So you need to have, the particles need to be pneumatically aligned in order to generate stresses in these systems. Okay, so that's our basic model, and a few years ago we applied it to think about bulk suspensions. I'm just going to review the main results and then move on to confinement. So what happens in the bulk? The way you can explain the collective motion that is seen in the bulk is by doing a linear stability analysis of the uniform isotropic state. If you have a suspension that's completely uniform and isotropic in orientation, then you perturb it, what kind of perturbations are going to be amplified. So you can do the analysis, and this is the main result. So here I'm showing you the real part of the growth rate, so that's the actual growth rate, as a function of the wave number k of the perturbation that you're imposing, and what you find is that there is a long wavelength instability, so positive growth rate at low wave numbers, which only occurs in the case of pushers. If you do the same calculation for pullers, the curve is negative. So there's a long wave instability. You can actually calculate everything by hand for this point right here, right, at k equals 0. You can figure out what the growth rate is, and for this growth rate to be positive, what we find is the following criterion, which is that alpha, which is a dimensionless dipole strength, which also includes the concentration, has to be below a certain negative value. So you need to be a pusher, you need to be sufficiently either concentrated or exert a stress which is sufficiently strong in order to induce an instability. There's another interesting point in this curve, which is this one. In order to have an instability, your system should be large enough that you're covering this range of wave numbers. So that gives you a criterion on the system size. And more precisely, the system size normalized by the particle size times this quantity, which is essentially the volume fraction, has to exceed a certain threshold. So you need a large system or a dense system in order to see collective motion. And indeed, in experiments on bacteria, it's always above a certain density that you start seeing collective motion. A couple more details. If you look at the maths, you can show that the instability actually pertains to the pneumatic bend mode, so the off-diagonal components of the pneumatic order parameter. Okay, so this is what happens in the bulk. We also tested it using simulations. I'm just going to show you a couple of movies. So these are systems of finite size, and we're increasing concentration from left to right. These are two pusher simulations and one puller simulation. In dilute suspension, the pushers, not much happens. They more or less all go in a straight line, deviate a little bit because of interactions, but there's no clear collective motion. But if you increase the density here by a factor of 10, you go over the instability threshold and you start seeing collective motion, which at least to the eye looks a lot like what is seen in experiments in bacterial suspensions. And the critical density above which this happens matches quite well what our theory predicts. Finally, just for sanity check, if you do the same simulation with pullers, there's no collective motion even at high densities. Okay, so this is our story for the bulk. I should mention that here we entirely neglected steric interactions between swimmers. These likely become important at high densities. So all I described here is purely due to hydrodynamics. Okay, so now let's think about confinement. And first I'm going to show a few slides about what happens in dilute confined suspensions, and then I'll move on to collective motion confinement. So you can take the same equation that I derived a few slides ago and simplify them to look at a dilute suspension. So you forget about the flow, there's no hydrodynamics anymore. And here we're going to be thinking about the following situation where the particles are confined between two flat plates. So that's a Healy-Shaw geometry. So this is what the Smolchowski equation that I had a few slides ago looks like in this case. So we're thinking about steady state. Here, if it's dilute, the distribution only depends on z as well as theta, which is the angle with respect to the wall normal direction. And this is what the equation simplifies to. We simply have a balance between self-propulsion, so swimming, translational diffusion, and rotational diffusion. That's it. No hydrodynamics. Here I've scaled the equations. I have a couple of dimensionless parameters. The first one is lambda, which is the ratio of the product of the diffusivities over the swimming speed squared. So this is a parameter which is specific to a particular type of swimmer, and we're going to keep it fixed and not worry about it too much. The one that's more interesting is this Heke number, which is essentially a measure of confinement. You can think of this as the ratio of the persistence length of the swimmer trajectories over the channel width. So when Heke is large, you have a very, very narrow channel. When Heke is small, you have a wide channel. Finally, we have to specify some boundary conditions, and these are quite critical. The boundary condition, which makes the most sense, is no translational flux in the normal direction at the walls. And this translates into this condition right here, which is a Robin boundary condition. And all this says simply is that there is a balance between swimming and translational diffusion at the wall. Okay, so we can solve these equations. You can do it by hand, but you can do it numerically. And lo and behold, this is what you get. So remember, I didn't put any hydrodynamics in the model, so the dipole wall interaction that I discussed at the beginning are not present in this model. And yet you still get accumulation at the walls, right, which is what is seen in experiments. This accumulation at the walls is also accompanied by a wall normal polarization, meaning that near a particular wall, particles tend to point towards the wall on average. So what's the mechanism if it's not hydrodynamics? It's a lot simpler. If you have a particle that's put between two walls, unless it swims exactly parallel to the walls, it's going to end at a wall, right? And when it's there, it's going to stay there until diffusion allows it to escape. Right? So it's very basic. Of course, if you add hydrodynamics to this, it would change the profile quantitatively, but not qualitatively. Okay, so we can explain accumulation with our model. That's good. Now we can also think about what happens if you add a flow to this, and I'll be brief here as well. So we're thinking about putting a Poiseuille flow here in this same geometry, still in the dilute case. So this is what the equation looks like now. We have one additional term, which corresponds to the shear alignment of the particles under the imposed flow. So this comes from Jeffrey's equation. And you can again solve this numerically. There's one more dimensionless parameter in this case, which I'm calling the flow Heke number, which is the ratio of the wall shear rate over the rotational diffusivity. And this is the usual Heke number that you would use for passive suspensions. So you solve these equations, and one thing that we see, which is also seen in experiments, is that there's a centerline depletion that occurs when you apply a pressure-driven flow. So here I'm showing you the concentration profile. I'm not showing the walls, so the walls are out of the frame here. I'm showing near the center of the channel, and what you find is that when you increase the flow rate, there's a depletion that occurs near the center. And this is something that was also recently seen in experiments from Roman Stocker. Very briefly, what's the mechanism? Near the center of the channel, the shear rate is 0, so orientations are more or less isotropic. Particles can swim in any direction they like. So particles are near the center, they're not feeling any shear, so they can swim away from the center. When they swim away from the center, they enter high shear regions and they become aligned with the flow. And when they're aligned with the flow, they're trapped. They can't cross streamline anymore. Right? So particles near the center, swim away from the center, and become trapped in high shear regions. This is what's causing the depletion. One more effect I want to discuss in dilute suspensions is upstream swimming, which is something that some of you might have heard of before. If you put bacteria in a pressure-driven flow, they tend to swim against the flow. This has been seen in many experiments, and the mechanism is quite simple. Again, from our model, we can calculate the streamwise polarization across the channel, which is negative near the wall, so particles near the wall are swimming against the flow. And the mechanism is very basic. As I showed earlier, particles near the wall tend to point towards the wall, as shown in this diagram. Now if you apply a pressure-driven flow, shear rotation is going to align the particle in such a way that it swims upstream. So there's nothing complicated here. And you can actually calculate the mean swimming flux with our model, which is shown here. So the mean swimming flux increases with flow strength and then decreases again at high flow strength. And one interesting result that comes out of our theory is that the swimming flux is proportional to the excess concentration at the wall. And since there's always wall accumulation, there's always going to be net swimming against the flow. Now we can also think about the rheology of the system, and this will take us to the second part of the talk on collective motion. What happens if you think about hydrodynamics here? Here I neglected hydrodynamics entirely. Now let's think about the swimmer-induced flows. So I'm still in a channel, and particles, on average, tend to point towards the wall, but now they're inducing these hydrodynamic disturbances shown by the blue arrows. What happens if you apply a pressure-driven flow? Well, they're going to rotate. This is what leads to the upstream swimming. And what you can see here is that the disturbance flows that they're inducing are going to tend to enhance the imposed flow, right? The arrows near the flagella here are pointing in the same direction as the imposed flow. In other words, this bacteria are going to pump fluid in the same direction as the imposed flow, and this is equivalent to a decrease in the effective viscosity of the suspension. And you can write down a model, actually, and calculate the effective viscosity in this geometry, which is shown here on the right as a function of flow strength. And typically what we find is that at low flow strengths, in weak flows, there's a viscosity which is less than 1. 1 is the viscosity of the solvent. Then it increases with flow strength, exceeds 1, and then shear thins again at high flow strength. Is this real? Yes, it is. There have been a few experiments recently looking at the effective rheology of bacterial suspensions, and they get curves that are quite similar to what we obtained in our model. One very interesting prediction, though, is that if you increase the density, which is what's shown here on the top plot, the low shear rate plateau decreases until it reaches 0. So at sufficiently high densities, you get a viscosity which is 0, and that's superfluid. Right? And we're not the first to think about this. This was first described in the experiments of Lopez et al. Last year. So at sufficiently high densities, you have a fluid with 0 viscosity, and this should lead to spontaneous flows. And so this takes me to the rest of my talk, where I'm going to be thinking about collective motion in confinement. So we're going to look at this numerically without going into the details, but we're solving our equations for the moments, so the concentration, polarization, and magnetic order parameter. These equations, you can derive them from the Snow-Chowsky equation that I showed you earlier by taking moments and making a few approximations. So the ingredients are the same. We have fluxes here, which come from convection by the flow, swimming, and translational diffusion. We have a number of source terms here that account for rotation of the particles by the flow, and the last two terms here on the right-hand side account for rotational diffusion. This is coupled to Navier-Stokes, where we again have the active stress term, which is proportional to the pneumatic order parameter tensor D. Let me remind you of the parameters that are important in this problem. So we have a Reynolds number here, which we keep very small. It's not particularly important. The two parameters that are the most interesting are the swimming Peclet number, which again is a measure of confinement. When this is large, the bacteria are very strongly confined. And this parameter alpha, which denotes activity, so it's the dipole strength times the concentration compared to the viscosity and rotational diffusivity. And this is a negative parameter for pushers. Okay, so let's see what we see. First, we're trying to reproduce the experiments of Yolande that saw the double vortex in these squeezed bacterial drops. These are two-dimensional simulations, I should say. So we're first looking at circular disks, and this is what we see. We see three different regimes depending on the values of the parameters. In either very dilute suspensions or very strongly confined suspensions, we find an equilibrium regime in which the particles simply accumulate at the boundary, and at the boundary they have a net polarization towards the wall. This is the same wall accumulation that I discussed in the Healy-Shaw geometry. As you increase activity or increase concentration, same thing, or if you slightly decrease the domain size, you transition to a second regime, which is precisely the double vortex that was seen in the experiments of Yolande. So this is a model. We're starting from the equilibrium solution, and we're letting it go. And this is what it looks like. It's a bit hard to see. There are streamlines actually that are superimposed, but let me play it again. There is indeed a double vortex that forms. So there's the center that rotates in one direction, and near the walls it's rotating in the opposite direction. I'll show you more details on this in just a second. Finally, if you keep increasing activity or decreasing the size of the domain, you reach an unsteady chaotic regime, which is similar to what you observe in bulk suspensions. So there's no equilibrium configuration in this case. There's strong mixing, just like you get in 3D. So you can draw a phase diagram for these different regimes, and this is what it looks like. So here the vertical axis denotes activity, and we're thinking about negative values of alpha. So when you move down, you're becoming more and more active or more and more dense. And the horizontal axis is confinement. When you're moving towards the right, you're going to a smaller and smaller domain. So these are our three regimes. So you have equilibrium in very confined dilute systems, and then it transitions to the double vortex, and finally chaos. And the black curve here is a prediction from a linear stability analysis of the equilibrium state, which I'll show you more details about in just a second. If you want to be more quantitative, you can define an order parameter here in terms of the velocity. This order parameter phi is approximately -1 at equilibrium when everything is radial. It jumps to +1 when everything becomes azimuthal, the motion becomes azimuthal, and then it goes to square root of 2 minus 1 when it's chaotic, and you get what you expect. If you plot phi as a function of alpha, you start from -1, you jump to +1 when you're in the double vortex regime, and then down to square root of 2 minus 1 when you're reaching chaos. So the double vortex, it really looks like what is seen in experiments. Here you can see the streamlines a little bit more clearly, and you also have profiles on the right. If you look at the fluid velocity, actually the fluid velocity does not show double vortex. It's a single vortex. It always goes in one direction. But if you look at the net particle velocity, which is fluid velocity plus swimming velocity, this one changes sign. So near the center, it's moving with the fluid, but near the wall, the bacteria are moving against the flow. And the reason for this is quite simple. If you look at the polarization, the bacteria, in fact, aligned against the flow everywhere. So they're swimming against the flow, and the mechanism is the same as the mechanism for upstream swimming that I discussed previously in the case of the channel flow. As I mentioned, we can actually predict the transition from equilibrium to the double vortex using a linear stability analysis, and I'm showing a few results here. So we're just linearizing the equations about the equilibrium state, and what we find is that there's actually an infinite number of unstable modes that can become unstable. The first one is a double vortex, which has the characteristic velocity field shown here, and then you have higher order modes which correspond to alternating layers of fluids going in opposite directions. And if you look at the marginal stability curve for this instability, for mode 1, it matches the transition from the equilibrium state to the double vortex quite well. Okay, then we can start looking at more complex geometries, and I'm going to show you a couple of different cases. We can think about an annulus to reproduce the experiments that were done in periodic racetracks. And in an annulus, you get somewhat similar dynamics, but there's one more regime which we observe here, which is the gray dots, in which you have traveling waves. I'm going to play you the movie. So first, let me go over the other regimes first. So we have equilibrium, which is no flow, everything accumulates at the walls. You increase activity, and you jump to a state with net pumping. So there's net flow in one direction, right, which is similar to double vortex. But then we have these traveling waves, which is the state, the regime 3 here, where you still have net pumping, but you find density waves that are propagating with the flow. And finally, in very, very active systems, you get chaos with no particular direction. Once again, we can predict the transition from equilibrium to net pumping using a stability analysis, and just like in the previous case, there's actually higher order modes that are not observed in our simulations. A couple more examples. So these are very similar to the annulus, but these are now racetrack geometries, which were the ones used by Violon in his recent paper. So same 4 regimes. This is the base state where the particles simply accumulate at the wall. Actually, I think you already had the flow in this one. This is the one when you restarted. So first they're going to go to the wall, and then the net pumping is going to start. Oops. It's hard to see the pumping here because it is there's no waves. But if you increase the width a little bit, you're going to start seeing the traveling waves that I mentioned earlier. These become even clearer in wider channels. And finally, if it's very wide, you get chaos again. If you try to compare this more quantitatively, well, it's still qualitative actually, but more precisely to experiments, you can look at the streamlines in the different regimes, and they match the experiments quite well. So this is a unidirectional flow where you don't see any waves, and the waves start to appear, and eventually you get alternating vortices, and this transitions to chaos. Last point I want to make is relate these spontaneous flows to the result that I showed you on the rheology, the fact that these suspensions can behave as superfluids. So what we think is that these transitions to net pumping are due precisely to the fact that the viscosity becomes 0. Can we test this more precisely? The answer is yes. So what am I showing you here? First on the left, I'm comparing the low flow rate viscosity. So this was the low shear rate plateau that I showed you in my rheological results earlier as a function of alpha, which is activity or concentration. Right? So when you're increasing activity or concentration, the viscosity decreases until it reaches 0. And the point where it reaches 0, it's kind of hard to tell the colors apart here, the point where it reaches 0 coincides exactly with the marginal stability of the equilibrium state. In other words, the transition to equilibrium to net pumping coincides with the transition to superfluidity. So it's the viscosity becoming 0 that leads to these flows. And another way to think about this is that if it is indeed a flow that has 0 viscosity, then the speed of the flow should not depend on the length of the channel. Right? And this is something that we tested very recently. So what we're doing here is calculating the net flow rate in the pumping regime as a function of the length L of the channel, which is normalized by H. H is the gap width here. And what you see is that going from 0, which corresponds to the annulus, to 15, which is a very long channel, the flow rate essentially remains constant. Look at the vertical axis, this is 2.7, this is 2.8, right? So these flows are frictionless, right? You can increase the length of the channel, they're always going to flow at the same speed, and that's because the viscosity is 0. Okay, let me just conclude by showing you a couple of movies in more complicated geometries. So we're starting to look at 3D. These are all two-dimensional simulations, and here on the left is simply a movie of the dynamics inside a sphere, where what you're seeing is the streamlines, and what you find is that in a sphere, you get the formation of a large vortex as well, which is a little bit harder to visualize than in 2D. And on the right, what I'm showing is an array of connected chambers. So these are little circular chambers, and they're connected by these junctions. And what we're trying to look at here is whether they're synchronized or not. If they were isolated, you would get double vortices going in random directions. But because they are connected, what we find is that they end up all synchronizing except near the edges, but at least in the center, and spinning in the same direction. This is something that was also seen recently in experiments by Rheological. We're still in the process of analyzing this more precisely. In the experiments, at least, they found that there was a very strong sensitivity on the geometry of the junctions, and they could either all synchronize or anti-synchronize, so we're still exploring this. Okay, just to summarize. We've been thinking about confinement, and what we find first in dilute systems is we can explain wall accumulation simply as a result of the balance between swimming and diffusion, so you don't need hydrodynamics. And in pressure-driven flows, we're able to explain the depletion of the center line and the shear trapping, which are observed in experiments. Now, if you concentrate the suspensions, they still undergo a transition to collective motion, but this collective motion is very different than what you see in the bulk. In particular, in circular disks, what we find is the existence of this double vortex, which is also seen in experiments, where you have this counter-rotating boundary layer. And in periodic channels, there are also spontaneous flow transitions, which lead to net pumping. And what we've shown is that the transition to net pumping coincides with the transition to superfluidity. All right, let me just finish by thanking the folks who did the work. So Maxime, my postdoc, is right here. He's the second on the right, and he did almost all the simulation that I showed in the second half of the talk. The theory was done primarily by Roberto as well as Barat, and my funding came from the NSF. Thank you for your attention.
I can be loud. So I'm not a fluid person, so I may be being dumb. So if I have a pipe and the pressure difference across it, the resistance goes like the length, right? So I make the pipe longer. If I don't see the flow rate change, you imply the viscosity 0. In your system, I make the length longer, but that the number of swimmers I have is in some sense proportional to the length, right? Because you fill it. And so the amount of energy you're burning is proportional to length. So I'm a little confused about this conclusion that that really means it's at superfluidity in that case, because the flow rate is 0.
Okay, you're right about the energy, yes. Think about this. Yes, I see your point, actually. So what happens is that the suspending fluid viscosity becomes irrelevant, I guess. The viscosity of your liquid phase becomes irrelevant. Essentially, it's completely balanced by the active stresses. But you're right about your point that it's not like comparing keeping pressure constant and increasing the length of the pipe. Yeah.
Yes. I would like to ask you again about this zero viscosity thing. Mm-hmm. I guess there are two things. One is the viscosity of the resistance to flow, And then the other thing that you showed us is that there are some waves, some density waves. I wanted to ask about the dissipation mechanism for those density waves.
Oh, so we really have not looked into the waves too much, to be honest. They're a lot harder to analyze because you have to, all the theory that I showed was 1D essentially, right? And now you have to do look at the 2D theory, so we haven't looked at that in detail yet. Can I ask another one?
You have this vortices, one rotating one way.
Mm-hmm.
Are there cases in which the bulk stays fixed and the thing flows only at the edge?
We've never seen that, no. You need, so let me go back. So the mechanism again for the double vortex is the following. So if you introduce a flow perturbation, which is azimuthal, right? This is going to align the particles in such a way that the stresses that it generates reinforces the flow. And this alignment is such that the particles actually point against the flow. Right? This is like the upstream swimming that you have in channel flows, right? But you need the fluid flow in order to sustain the alignment. So I don't think you could have the counter-rotating boundary layer, which comes from swimming, without having the fluid flow going in the opposite direction.
What if the system was not self-propelled?
Oh, it was not self-propelled. So, for example, like microtubules and molecular motors or something like that. I think you would see, well, I know that similar effects have been seen in the experiment by Dojic. But in this case, it's the same idea. What aligns the microtubules is the flow. So you need something that aligns the particles. You might be able to see it at very high densities due to steric alignment, I should say. Here we're only thinking, and the only mechanism for alignment here is hydrodynamic.
So if there are no more questions, that's the, oh, there is one more.
Just two short questions. I'm all the collaboration. You showed the strength of dipole very precisely, 7.98.
I was wondering, 10 to the minus 19.
Okay.
I was wondering what specific model produces this thing.
So this is just a fit, a numerical fit, right? We took the flow field for a point dipole. Well, we didn't, I should say. It was done in this paper, and it was fitted to the actual flow field measured by PIV, and from this you can extract the only free parameter, which is the dipole strength.
Okay, and the other question is, in your model of wall accumulation, so the results might depend on the rate of tumbling. Did you check that?
Okay, so I should say in everything I showed you, we did not include tumbling, actually. We included rotational diffusion, right? Which has similar qualitative effects, it's not quite the same thing. As it turns out, actually, the wall accumulation layer in our model depends on the translational diffusion, mostly, not so much on the rotational diffusion. Let's see, what is that? So in fact, the thickness, I mean, at least in this model, the thickness of the layer scales primarily like the swimming Peckley number times this type of, this should be lambda.
But that changes if it's tumbling, then it totally decorrelates.
But I mean, in the absence of hydrodynamic interactions, the persistence of the dynamics that comes
depends on the rotational diffusivity, that's right. Yeah.
Is critical to get
if you don't have any orientation decorrelation at all, of course, the particles just condense at the boundaries.
Well, but even if you do, I mean, if there's no hydrodynamic interaction, if your rotational diffusion is alive, and then the particles behave firmly.
That's right. Yes.
So you don't get this.
That's correct.
So it is.
In fact, I think I don't have a curve here. So the Peckley number here that I'm using as a measure of confinement involves the rotational diffusivity, right? And if the Peckley number becomes very large, what happens is that the two boundary layers merge and you get a uniform profile. So essentially, you no longer get accumulation.